Section 7.5, Partial Fractions. There are still some classes of integrals that none of our previous techniques will resolve. For example, consider the integral of 1 over x squared minus 1 dx. If you were to try a u substitution or parts or a trig substitution, none of those would resolve this integral. So the idea here is that we need to use a little algebra to help us out. And notice if we write 1 over x squared minus 1, we factor the denominator to get 1 over x plus 1 times x minus 1. And then if we were to split this rational function into the sum of two rational functions, each of which, notice the denominator here is one of the factors in the denominator here. The denominator here is one of the factors in the denominator here. You can think of this as a reverse common denominator process. In algebra, you're used to taking this, getting a common denominator, and simplifying it to get this. But now we're playing the game backwards. Instead of combining things into one, we're splitting one into several, if you read this from left to right. Now, I've just declared to you that the coefficients, the numerators here that make this equality true are a minus 1/2 and a 1/2. In general, we wouldn't know what these are. We'd have to figure out what they are. But you can check me. If you were to combine these two, get a common denominator, and combine these two, you would see that this is algebraically equivalent to this. Okay? Now, if you just set to the side for a moment of how I got those numbers, and you just see what having those numbers does for us, then if this expression is equal to this expression, then the antiderivative of this is equal to the antiderivative of these two pieces. And notice each of these integrals, when we do this integral was intractable, but this integral is doable. We factor out the minus 1/2, we make the little u substitution, u equals x plus 1, and we antidifferentiate to get a minus 1/2 ln of absolute x plus 1. Similarly, over here, we can factor out the 1/2. We use a little u substitution, u equals x minus 1. We antidifferentiate. We get 1/2 ln of absolute x minus 1 plus a constant. The idea here, again, was that by splitting the original integrand, we traded one difficult integral in for two easier integrals. Okay, so the general idea of this is called a partial fraction decomposition, or a PFD for short. The setting for a partial fraction decomposition is one where you have a polynomial p of x divided by a polynomial q of x, where the degree of the polynomial p is strictly less than the degree of the polynomial q. Remember, the degree is just the highest power that appears in the polynomial. We want to look at several cases and see how the partial fraction decomposition theory tells us how to decompose rational expressions of different forms depending on what we see in the denominator, q of x. So case one, let's just suppose that q of x has distinct linear factors. So distinct, so none of them are repeated, and linear because they factor as linear functions. So for example, q of x, if it looked like x minus some number a1 times x minus some number a2, down to some x minus some number an, then notice each of these is a linear factor, and as long as the a1, a2 down to an are all different numbers, then none of these are repeated, so these would be distinct linear factors. When you have distinct linear factors, what the partial fraction decomposition theory says is that you're going to rewrite this rational function as a sum of rational functions. Each denominator in the terms over here are just the respective linear factors, and then the numerator is just some yet to be determined constant in the top. Let's look at how to do this with a concrete example, and I think it'll help a lot. So let's look at example 2. Suppose we have the integral of 3x plus 11 over x squared minus x minus 6. So if we take the integrand 3x plus 11 over x squared minus x minus 6, and we factor the denominator into x minus 3 times x plus 2, then case 1 of the partial fraction decomposition says that we should get a constant over x minus 3 plus a constant, a different constant, times or over x plus 2. So this is the partial fraction decomposition template for case 1, and now in order to find the constants a and b, let's multiply everything in the equation by the common denominator, x minus 3 times x plus 2. When we do that, both of these cancel and we get 3x plus 11 on the left-hand side. On the right-hand side, the x minus 3's cancel and we get a times x plus 2, plus when we multiply here, the x plus 2's cancel and we get b times x minus 3. Notice that this polynomial version of our equation is easier to work with than this rational version of our equation. We still need to find the numerical values of a and b, and I'll show you two methods for how you can do that next. The first method, which I'll call equating coefficients of like terms, is as follows. So what we do is we just have the left-hand side is what it is, 3x plus 11. The right-hand side, we just expand this out and we collect our like terms. So we get an a plus b times x, and we get a 2a minus 3b as our constant term. And the idea here is if this first degree polynomial is equal to this first degree polynomial, the only way that that can happen is if the coefficients of the like terms, so the coefficient of the x term here is 3, that must equal the coefficient of the x term on the right-hand side. So a plus b must equal 3, and similarly the constant term here must equal the constant term here, so 2a minus 3b plus must be 11. This gives us two equations and two unknowns. You can solve those by your favorite method, and when you're done, you'll get that a is 4 and b is minus 1. Now that we found the numerical values of a and b, we can return back to our partial fraction decomposition template. We can substitute in those values, and now we see what the numbers are for a and b that make this partial fraction decomposition, make these two equal. Now you can see how I got those numbers minus 1/2 and 1/2 in our first example. So that's one way to find the numbers. Notice none of that involved calculus. It was all just algebra. I'll show you a second method. Our book calls this the value substitution method. Often in engineering, this is called the cover-up method. So we'll begin at the same place with the polynomial version of our equation. We need to find a and b. And the idea here is, since this function of x is equal to this function of x for all values of x, then we can pick any value of x that we want to, and as long as we plug it into both sides of the equation, those must be equal. So notice if we make a clever choice for x, we can actually make our life computationally much simpler. For example, if we pick x to be minus 2 here, that will zero this term out. If we pick x to be 3, it would zero this term out. So why don't we pick x to be minus 2? When we plug x to be minus 2 into the left-hand side, we get 3 times minus 2 plus 11, which gives us a 5. When we plug minus 2 into the right-hand side, we get a times minus 2 plus 2, so that's a times 0, minus a 5 plus b times a minus 2 minus 3, which is minus 5b. You can see why they call this the cover-up method. If we were working together on a marker board, this value of x that when we plug in, it covers up or it makes this vanish. It goes away. It becomes a 0. And we just get 5 equals minus 5b. So very quickly we get that b is minus 1. So one constant down, one still to go. We need to make a different choice for x. Here we'll pick x to be 3 because it's going to cover up or make this term vanish. When we plug a 3 in here, we get 3 times 3 plus 11, which is 20. When we plug a 3 in here, this vanishes, and we just get 5a. So that says a must be 4. Notice we got the same numbers as we got using the last method. This is just a little bit, I think, a little bit quicker, a little bit more efficient, but feel free to experiment with both methods and use whichever one resonates better with you. At the end of the day, we just need to know what the template was, and then we need to find the values, whichever method we choose. We need to find the values for the constants. When we find the values for the constants, then we have the partial fraction decomposition. Now, back to the calculus. If this function is equal to this function plus this function, then the integral of this must equal the integral of this plus the integral of this. That's what we have in blue. Notice we've traded in one complicated integral in to get two easier integrals. And this is sort of the moment of truth. Hopefully these integrals are going to be easier to do, and they are, because these are simpler rational functions than the original rational function. This you can either do in your head or do with a little u substitution. U is x minus 3. You get this as an antiderivative. Here you can do this in your head or do it with a little u substitution. U equals x plus 2. And we get minus ln of absolute x plus 2 plus an arbitrary constant. Okay, let's take a look at case 2. What happens if q has a repeated linear factor? So not just a linear factor, but one that's repeated. And this would look like a p of x over, say, an x minus a number to the n. This n is the number of times that this linear factor is repeated. In algebra theory, this is called the multiplicity of this factor. And so what the Partial fractions theory says is that if you have a repeated linear factor, then you should get terms, I think of it this way, you should get terms whose denominators count up on the powers of that linear factor until they're all exhausted. And then the numerators of those terms are just their own individual constants. Let's look at a concrete example. If you have the integral of 1 minus 2x over x plus 1 quantity cubed, we look at this. This is a linear factor. It's repeated. It has a multiplicity of 3. So what we're going to do is have 3 terms. We're going to have an x plus 1 to the first power term, an x plus 1 to the second power term in the denominator, and an x plus 1 to the third power term in the denominator. So when you're writing these out, you'd write this out. And then you know every one of those terms has to have their own constant in the numerator, and they do have to be different constants. So this is the template for the partial fraction decomposition in case 2. Proceeding just like we did before, we're just going to multiply everything in sight by the common denominator to turn this equation into this. Notice here all the powers of x plus 1 quantity cubed cancel. Here one of the powers cancel and you're left with 2. Here 2 of the powers cancel, you're left with 1. Here all 3 of the powers cancel and you're left with just a c. This polynomial version is easier to work with than this rational version. And now using the cover-up method, we just make judicious choices for x. We see pretty quickly that an easy choice for x would be minus 1 since it's going to zero out this term and this term. So let's start with that one. And if we plug an x equals minus 1 in, on the left-hand side we get a 3. On the right-hand side we get a 0 and a 0 and a c. So we get c is 3. So 1 constant down, 2 to go. Now notice if you look at this, there are no more clever choices for x that are going to make things just zero out. And this oftentimes happens in partial fraction decompositions. You use up all of your easy choices, and then you just have to make some choices. I normally try to pick numbers that are pretty easy to plug in, like zeros or ones or twos or minus ones. But we know we're going to have to make 2 choices because we still have 2 more constants to find. So I'll just pick x to be 0. If I plug this into the left-hand side, I get a 1. If I plug this into the right-hand side, I get an a times a 1 plus a b times a 1 plus a c. But I already found that c was 3, so I'll substitute that in. If we stare at this, if we throw the 3 to the other side or we rearrange, we get one equation in 2 unknowns. So we get a plus b is minus 2. We just need to be patient. Let's make another choice. I'll just pick x to be 1. If I pick x to be 1 here, I get 1 minus 2 times a 1, so I get a minus 1 on the left. On the right, I'm going to get a 4a plus a 2b plus a c. My c is 3. When I look at this, this is one equation and 2 unknowns. I throw the 3 to the other side and I rearrange, and I get 4a plus 2b is minus 4. So now I have these 2 equations and 2 unknowns. If I put them together and solve this 2 by 2 system, you can do that using the method of your preference. It turns out that we'll get the a is 0 and the b is minus 2. Make sure that you can do this and that you're comfortable with doing this. All right, so now we've found the constants for a, b, and c. Let's return to our template. Let's put the value of those constants in. And the algebra is now done. We can turn back to the calculus. If this is equal to this plus this plus this, then the integral of this must equal the integral of this plus the integral of this plus the integral of this. And the idea is hopefully this complicated integral, we traded it in for 3 integrals that were easier to do, and definitely we did, because this comes out to be a 0. Here, if we make the little quick substitution, u is x plus 1, we turn this into a doable u integral. If we make, I'll use a different letter since these aren't the same, necessarily the same. I'll say w is x plus 1. We quickly, I'll let you do the details here. We turn this into a w integral. This is just a power rule. This is again just a power rule. We add our constant of integration and then we substitute back. It would be totally fine with me to stop right here, or you could rewrite it as this in this form. Okay, so the idea once again is once we know the template, we use the cover-up method to find the coefficients, and then we integrate the pieces. Hopefully the pieces are easier to integrate than the overall original function was. All right, let's look at case 3. Case 3 is when q of x has an irreducible quadratic factor. Irreducible quadratic factor means it's a quadratic factor and it can't be factored any further over the reals. So just because it's quadratic doesn't mean it's an irreducible quadratic. So you always want to check if it can factor further over the reals. So in general, this would look like a p of x over some ax squared plus bx plus c, where this doesn't factor over the reals anymore. And the partial fraction theory says that when you go to do this, you should have your irreducible quadratic in the denominator. And this is where it's different from cases 1 and 2. When you have a quadratic in the denominator, your numerator, irreducible quadratic in the denominator, your numerator is going to be an arbitrary linear function. So an ax plus b. Let's look at a concrete example. Example 4, we have integral of 2x plus 3 over x minus 1 times x squared plus 9. One thing to note is these cases can be combined. You can have a case 2 mixed with a case 3, mixed with a case 1. This can happen. And so I'm showing you one here. This is a distinct linear. It's linear and it's not repeated. This is an irreducible quadratic, and make sure you understand why. This cannot be factored further over the reals. A telltale sign of when a quadratic is irreducible is if it's in this form, then you can just check its discriminant, b squared minus 4ac, and if the discriminant is negative, it's an irreducible quadratic. Okay? So we're going to use our partial fraction decomposition theory, and we're going to just strip out the integrand. The template is we should get a term here with our distinct linear factor in the denominator. We should get a term here with our irreducible quadratic in the denominator. And then for this distinct linear, we should get a constant in the numerator. For this irreducible quadratic, we should get a general linear function in the numerator. So this is our template for case 3. We'll multiply through by the common denominator. When you do, this equation becomes this. This polynomial version is easier to work with. Now we'll use the cover-up method. We have 3 constants to find, so we know we have to make 3 choices. We immediately see that x equals 1 will be a nice cover-up method choice because it will zero this entire term out. So we'll pick x to be 1. On the left-hand side, we get 2 times 1 plus 3, which is 5. On the right-hand side, we get 10a. We get b times 1 plus c, but we're multiplying this times a 0, so this whole term is gone. We get 5 is 10a, in other words, a is a half. Now we have to make some more choices, and we've used up all of our clever choices, so we can pick whatever we want to. I'll just pick 0. That's easy to plug in. On the left-hand side, I get a 3. On the right-hand side, I'm going to get a 9a. I'm going to get a b times 0 plus c, multiplied by a minus 1. So that's just going to give me a minus c. I already know that a is a half, so I'll go ahead and plug that in. And when I solve this for c, I get that c is 3 halves. So 2 down, 1 to go. I need to make one more choice. I'll just pick x to be minus 1. If I put x to be minus 1 in here, I get a 1 on the left-hand side. On the right-hand side, I get a times a 10. Then I get a b times a minus 1 plus a c, all times a minus 2. But I know that c is 3 halves, and I know that a is 1 half. So when I substitute those in, and I rearrange and solve for b, I get that b is negative 1 half. Okay, so when all the algebra is finished, I know that my template looks like this, and I found the numerical values of a, b, and c to be 1 half, minus 1 half, and 3 halves. So since this function is equal to the sum of these two functions, the integral of this must equal the integral of this plus the integral of this, and that's what we have in blue. And now we take stock of our integrals. These should be doable. This is very straightforward. We pull the 1 half out, and we either do this in our head or using the little u substitution, u is x minus 1. We anti-differentiate. Now here, this is a little bit more complicated. When you have this linear function with 2 terms here over this irreducible quadratic denominator, typically what you want to do is you want to split this, and you want to do the minus. You basically want to do the bx over the quadratic, and then you want to do plus c over the quadratic. So here I have a minus 1 half x over x squared plus 9. I'll go ahead and pull the minus 1 half out. And then I have a 3 halves over an x squared plus 9. I'll pull the 3 halves out. So this always splits into 2 integrals. Just algebra, no calculus. Like I said, we already anti-differentiated this. You can do this with a very straightforward u substitution. And you can do this recalling the integral from calculus 1, that the integral of 1 over x squared plus a squared is 1 over a tan inverse of x over a plus c. So this is a tan inverse integral. Okay, so that's how we handle case 3. And I guess the last case is, in case 4, what happens if Q has a repeated irreducible quadratic? So if you have a repeated irreducible quadratic, we won't do theory here, we'll just show you with an example. So imagine we had 1 plus 3x squared all over x times x squared plus 4 quantity squared. Notice this is a distinct linear factor, so this is a case 1. This is a irreducible quadratic. You can check its discriminant is negative. You can also check that it doesn't factor any further over the reals. And it's repeated because notice it has a multiplicity of 2 here. So this is a repeated irreducible quadratic. So what the theory says, well, we know how to handle the distinct linear. You should get that linear factor with its own constant in the numerator. When you have a repeated irreducible, it's going to be in the same theme as case 2 when we had a repeated linear. Remember what we did with our repeats. We took whatever was repeated, we counted up on our powers until we hit our multiplicity. And then the numerators, since this is an irreducible quadratic, this should be, what is the numerator for an irreducible quadratic? It's always a general linear function. So we've already used a, so this should be bx plus c. Notice we're counting up on the powers of our irreducible quadratic. When you have an irreducible quadratic, your numerator is a general linear function. So I need to put a different general linear function here. I've already used bx plus c, so how about dx plus e? And if this had been a 3, we would have had a third term. Its denominator would have looked like if this had been an x squared plus 4 to the third. We would have had a third term added on, or a fourth term added on, sorry. And its denominator would have looked like x squared plus 4 quantity cubed. Its numerator would have been another general linear function, so maybe an fx plus g. And so the ideas from here are the same as the last examples. Really the newness is what is the template for the partial fraction decomposition when you have a new case. And so we're seeing that this is how you handle a repeated irreducible quadratic. You would use the cover-up method to find the a, b, c, d, and e. Once you know those numerical values, you would just find the integral of this. You would just integrate these pieces. This is going to be a straightforward integral. This looks like the ones from the last example where you would need to split it into 2. And this is one where a u substitution should work for you. Okay? So I tried to give you a look at several examples from all of case 1, 2, 3, and 4, sometimes where the cases are mixed together. Give this a try in the homework and see how it goes for you.